it is the last topic in chapter 4, the base rule. You can Google who is the base. So let me Google for you. Thomas Base. He was born in 1701, more than 300 years ago. About 300 years ago, he suggested the base rule. Yeah, very old rule in statistics, in history. But it was, 300 years ago, it was a big finding. Yeah, it's fantastic. It is fantastic. So the base rule is the last topic in chapter 4. And I guarantee it is the most difficult one. How do you feel? Chapter 2, chapter 1, chapter 2, chapter 3, and chapter 4 so far. Not bad, right? It's getting harder. More topics, but not bad, right? What did I say? It is the most difficult one. What do you expect next from chapter 5? Getting easier. It's getting easier. Even though we are going to discuss more topics, the new topics. But it's getting easier and easier. Do you know why? Because we are going to do again and again and again. So trust me, it is the most difficult one. It's almost done. Go over the hill, we are going down. Okay? So keep going. So let me suggest to you, let me teach you what is the base rule. For the base rule, the very first, I have to give you the Venn diagram again. Yeah, it's a probability. It's a Venn diagram. It's the last topic in chapter 4. So here's a rectangle. And then we are going to separate the sample space with some partitions. It will be A1, A2, and so many A's. So let me say the AK. Here. They are mutually exclusive. Do you remember the mutually exclusive again? When we discussed the special addition rule, mutually exclusive, no common area. Please look at the Venn diagram. I just made the partitions A1, A2, A3 separately. No common area. Mutually exclusive, yes. Bless you.
Thank you.
And the next one, exhaustive. How do you think? What is exhaustive? That means, I'm sorry, I have to using the notations for mathematical notations, the union. The union all A's. Let me write again. I don't like it. Union all A's. It will be the sample space. What I'm saying, we can partition all sample space. Yeah, please look at the Venn diagram. Yeah, that is mutually exclusive and exhaustive. That is the mutually exclusive and exhaustive by AIs. Simply I can say when I have a male or female, then I just separate two parts, the sample space. Before we had an example, 40 students. 17 male, 23 females. Only two groups, male, female. So now I can say it's A1, male, A2, female. A's, mutually exclusive and exhaustive. So can you understand what is the mutually exclusive and exhaustive? It's good, right? And now we have another event, B. Like this. Here's a B. So we have to understand the base rule is based on this kind of Venn diagram. Many A's, but only one B. It's good? Okay? Let me bigger. Mm-hmm. You know, it is not the base rule. It is not the base rule. Who is this? The rule of total probability. So we can take the total probability. Okay, let me see the formula. Ugly. Probability of B. We had many A's and only one B. The probability of B, that is the total probability. We are going to take the total probability, B. How? Like this way. Ugly. I hate it. Let me erase the summation. Let me erase the index of J's. Yeah. Erase everything. It's fine. Please look at the multiplication. Probability of A times conditional probability B given A. Have you ever seen the multiplication before? When? Yesterday. Where? The general multiplication rule. Probability of A times probability of B given A. Who was that? By the multiplication rule, it was probability of A and B. Let me rewrite. It is probability A and B. By what? The general multiplication rule. A and B. Can I make smaller? Because I need the Venn diagram. Okay. Now we have a probability of A and B. Now let me add the index of J. Okay. Index of J was here on A. So let me plug J on A. You know, J is the index. It might be 1, it might be 2, it might be 3. Actually we had, it's not just A, but we had A1, A2, A3, up to AK. The subscript 1, 2, 3, 4, that is a J. So J might be changed. J might be changed. Sometimes it is 1, the very first one. Sometimes it is a 2, the second one. 3, third one. K, the last one. Good, right? So let me say again, It is 1. Now I can say it is 1. Please look at the Venn diagram. Where is the probability A1 and B? Here was the A1 and B. You know, before we had or, and. On the Venn diagram, where was the and? In the middle. A1 and B. You know, the J was the index. I told you it might be 2. So let me take the other one. A2 and B. A2 and B again. And. Where is the and on the Venn diagram? In the middle. A2 and B. If we take the A3, let me take the A3 here. And B, where it is? In the middle again. A4 and B, in the middle. Any other A's and B, always in the middle. In the middle, in the middle, in the middle. So now, what? We take the summation. We take the summation, all probabilities, whoever A and B, A1 and B, A2 and B, A3 and B, all KAs and B. Sum up all probabilities. It will be just in the middle. In the middle, in the middle, in the middle, in the middle. Who will be? Simply, it will be the probability B. I told you it's nothing. It is nothing. If you have an idea, it is nothing. What is the rule? Name? The rule of the total probability. For what? How can we get the probability B? We had only one B. In this way, you know, based on the Venn diagram, it's already the sample space was partitions by A's, and we added B. The probability B will be the summation. You know, it looked ugly, but now we can change. The multiplication was the probability of A and B, and sum up all kinds of A and B, it will be same as the probability of B. It's good? Okay? Okay, so it is the rule of the total probability. Now, base rule. Look at this. Worst. See? Yeah, it's the worst one. Okay? But still, the A's are mutually exclusive and exhaustive. So we are going to use the Venn diagram again. The sample space is partitions by A's, and we are going to have only one B. See? Here's one B. So even for the base rule, we are going to use the Venn diagram. Yeah. Please remember the Venn diagram. Yeah, the previous one. Okay, let me delete. Okay, it is too much. So first, let me delete something. It's almost everything, except the denominator. Have you ever seen the denominator before? Let me make the screen. It looks like this. Okay, good. How do you think? The denominator, the summation. Have you ever seen? When? Just before. Just before here. In the rule of the total probability. Please compare this one and this one. Yes, it is. Yes, it is. Good? Okay, let me rewrite. So now I can rewrite. It's something. Yeah, I raised the numerator. But the denominator was same as the probability of B. Just to say the denominator, the probability of B. By what? The rule of total probability. Okay, let me screen up because we don't need that. Yeah, we replace it. We replaced the denominator. It is the same as just the probability of B. Let me open. Okay. You know, oh yeah, good. Yeah. Let me clean up the numerator. Let me copy this one. Let me copy this one on the second equation, the probability. AI. Just a second before. Yeah. I have to change it. Okay. So please now look at this one. You know, just before when we discussed the rule of the total probability, it was, this multiplication was probability of A and B. By what? By the general multiplication rule. So I can rewrite, it will be probability A. Now it has AI. You know, the index might be sometimes J, sometimes I, J, K, L, M, and something, right? So let me just copy the AI because we had many A's. It's actually we had K A's and B. So far so good? What did I do? From here to here, by what? The general multiplication rule. From here to here, by what? The rule of total probability. Okay, now, look at this. Have you ever seen this one? Have you ever seen this ratio? Probability of what A and B over probability of B? Where? Can you remember what was the conditional probability rule? It was. Please go back to the note, your note, for the conditional probability rule. We used the joint probability. What was the joint probability? Probability of A and B. And use the marginal probability. What? Probability of just A or the probability of just B. We use the joint probability and the marginal probability. We define the conditional probability. Yes, it was the ratio for the conditional probability. For what? Then I can rewrite what given what. In the denominator, there is the event of B. So what given what? By the conditional probability rule. When you see the conditional probability rule, then the ratio will be A given B. Because whoever in a given part, it must be in the denominator. we have to take the marginal probability of the given event. Do you remember that? For the definition of the conditional probability? So the ratio will be A, the conditional probability of A given B. But you know, we had, it's not all A's, but one of the A's. So let me put the AI. Let me erase the left-hand side. Yes, it is. What? Probability. AI given B. Yes, we got it. How? We applied every single rules we had. It's from here to here, by the general multiplication rule, from here to here. Just before we got the rule of the total probability. And from here to here, by the conditional probability rule. So we applied 3 rules. We showed the base rule. The base, 300 years ago, he suggested the base rule by the 3 rules.
So it's all of those combined?
Yes, step by step. Here we applied this rule. There we applied another rule. Here is another rule. Finally, we can take this one. Nothing. Did you understand what was the multiplication rule? Yes. Conditional probability rule? Yes. How about the rule of the total probability? It's just before I show you A and B, A and B, A and B sum up will be same as the probability B. Yes. So we combine them together. And then finally, we take the conditional probability AI given B. Do you know why it is the fantastic rule in statistics? Please look at the left-hand side. What we got? Oops, sorry. The conditional probability of AI given B. Be careful. Focus on the order. A given B. Please look at the right-hand side. There is the B given A. B given A. From the B given A, what we got? A given B. Switched. It is the reason why 300 years ago it was a big finding. We can switch the conditional probability from B given A to get A given B.